It's a pleasure to be here. Mark asked me to come in and talk about some of the levee work that we're doing. We've gotten ourselves into the coastal arena here at CSU, which I'll expand on here in a little bit. Listening to me talk for 50 minutes can be quite nauseating, so if you have questions or thoughts or comments, please stop me beforehand. Mark said they usually serve food at these, so I don't see any. I don't have to worry about things being thrown at me, but let me know if you have a question and stop me, and we'll go from there. Know some of you, some fresh faces in here. A few of you think you maybe know me. Give you a little background on myself. I grew up, I think they called us rednecks affectionately, in western Pennsylvania on a farm. Oldest of 4 kids, and we had several of every different type of animal. You can see from my 5th grade picture that scholastic aptitude wasn't really my thing. By the time I was by the time I was released from high school, we'll say, I had probably built miles and miles of fence and could talk a horse into or out of almost anything, but higher education was not something that was in my future. Went into a chef's apprenticeship program, crazy Swiss guy, an 18-month program. You're literally a slave for that period. Anybody ever know who Gordon Ramsay is? This fella made him look like Tinkerbell. I mean, if we could have had those kind of TV shows back in the early 80s, I'd be on TV, but just not doing this. Had a number of restaurants back east and decided that the East Coast was, well, the East Coast, and wanted to move. My mother had listened to John Denver growing up, and before I realized that it was a crush that she had on him, we learned a little bit about the Rocky Mountains, and so loaded everything I owned into a van and drove out to Conifer, up just on the other side of Evergreen. Lived there for a couple of years and had a couple of restaurants up in the mountains and then down in Evergreen, and really liked it. My wife, girlfriend at that time, now my wife, bless her heart, pointed out to me very quickly that that wasn't the best life to have a family. Working when everybody else is on vacation and all the holidays and all the special occasions, and not being home to be part of the family was not really the best career choice. So I thought, well, I have residency, I like animals, I'll go to CSU and get into wildlife biology. And did. I started wildlife biology and realized very quickly that I'd given up a fairly lucrative career as a chef to maybe make $6 an hour as a temporary park employee. My wife came back into the picture and reminded me of these career choice decisions that I was making. So I really didn't know what to do, and looked through the course catalog and took a statics course. Just thought, what the heck, let's see what this is about, and loved it. It was like solving little puzzles. My simple little brain could get around the trig and around the simple algebra, and I just loved every bit of it. And thought, that's great, I'm going to design timber frame structures. That's what I'm going to do for a living. But needed a job. So I went out to the Engineering Research Center. Dr. Apt, who ran the research center at that time, then Lieutenant Colonel Apt, he's now Major General Apt, had posted a position for a work study. Well, I didn't have work study, and so I marched myself into his office, confident as can be. I think they called us hippies back then. I had a long ponytail I could tuck into my belt, a pierced ear, tie-dyed shirt, smelled like, well, never mind. And got into his office and asked him for a job, and he threw me out. And went back another time and asked him for a job, and he threw me out. The third time, he didn't know what to do with me and gave me a shovel and said, fine, come with me. Went out into the flume, some of you are familiar with, had 120 tons of sand in it. It's like a shovel. I know what to do with this. 10 days later, I emptied it out and was paid for my next job. I now run this place as director of the research center and director of the hydraulics lab. So if any of you have children or acquaintances or family members that you need the poster child for anything as possible, I'm it. I'm here to tell you that anything you put your mind to, you can do. Very fortunate what we do at CSU. As some of you are well aware, we're very big in the water business, hydraulic modeling. The folks that have, the Daryl Simons, the Rooming Lees, the Chester Watson, Stephen Apps, people that have come through that facility and left their mark on it, their work still gets referenced today. So it's quite a body of work that's come out of that facility. Typically, it's been all inland. What we've worked on is rivers and streams and inland applications. In August of 2005, that changed. We know what happened in New Orleans. Hurricane Katrina came in and absolutely devastated that area. While from space, it was a rather beautiful event. The aftermath and the destruction that was left on the ground is still being worked through today. There's places in the West Ward that are absolutely uninhabitable. You don't even want to drive through there, let alone walk. whole sections of that city are still completely rotting because of the effects of that storm. The infrastructure took a substantial hit, again, still being the event at the Super Bowl. Anybody watched the Super Bowl, the power went out. They knew that that was a distinct possibility because of the age and the water damage that had been done during that event. The infrastructure is what failed. The T-walls, the levees, the gates, mostly around the interface between a levee and a hardened structure. But nonetheless, they failed. You can see them trying to drop these sandbags in to stop that levee, kind of like the Dutch fellow with his finger in the dike. You know, it looks good maybe on paper, but it's not very sustainable. Areas where they had larger sections that came apart led to the unraveling of that entire system. It doesn't take much water to get in, or much of a breach for a city that's completely below sea level to fill up with water. Happens very quickly. And then not to have the pumping to get that out is a real problem. So what we thought we knew about that levee system and what we thought we knew about providing protection for overtopping, we realized very quickly there in the last week of August, first week of September, that we got caught with our shorts down. We really didn't have a very good idea of what the resiliency of the systems that we were recommending or we were employing for protection really was. Today, good bit of the levee system has been reconstructed. They've built it up to a higher elevation. It sinks anywhere from inches to feet a year, so they have to come in and put more lifts on top to be able to keep whatever that crest elevation is that we'll talk about here in a second, that is low enough to take up the smallest footprint, but high enough to provide the protection to the people that are living behind it. This is the Penn levee. It's been very well reconstructed, very well documented over the course of the last 5 or 6 years. You can see the top of the Penn levee. They put an eye wall in here, a concrete splash pad, and then they have vegetation. Vegetation grows down there. It's not like here where we can't get vegetation to grow. It grows out of concrete most places. So it's a very viable tool if you know how to design for it, if you know how to actually implement it and provide the resiliency. That's a buzzword, if you will, of how well the vegetation can absorb the hydraulic stress from a steady or an unsteady overtopping condition. Some levees haven't been treated at all. They've been constructed, they're in place. This is down by Houma, Louisiana. The levee's in place. You can see some grass growing on the top. They came in and put a lift of topsoil on their clay-filled levee. And it started to rain. And just the rain washed that topsoil away. Come to find out that the soil has so much salinity to it that we can't get vegetation to grow on it. Once that topsoil's gone, the soil isn't able to even populate vegetation. So the treatment has to match the field conditions so that we can come up with something that's actually usable. You can imagine if this were overtopped, the channelization that would occur, that levee'd be gone just like this. When the height's great, but it doesn't have any protection on it. Some areas they think are protected. This area is a section down by the Gordy pump station that has a turf reinforcement mat on it. Decent product probably, but it gets pulled up into the mowers and shredded. So just the operation and maintenance around that pump station has shredded this protection system, killed the vegetation, lost the reinforcement of the engineered product underneath it. So now the protection they think they have on paper, the guys back in the district in New Orleans, think that they have a factor of safety on this site, and they're nowhere near close to that because the solution that was implemented wasn't maintained properly. So it's not just the selection, the determination and the selection, but the operation and maintenance of that solution is paramount to the success. So we got a lot of tools available to us that we could use to protect levees. Some work, some don't. The key, of course, is to not have your protection system undermined. Willow plantings. Now, a lot of you probably know about bioengineering. Great for stream bank restoration, not so great for high energy waves. So being able to take the toolbox that we have and pull the appropriate tool out and apply it so that you don't have catastrophic failure and keep people safe is what this is about. So there's two pieces to overtopping components, as you well know, steady state and unsteady state. As an industry, as a body of knowledge, we know a good bit about steady state overtopping. We'll talk briefly about that, but there's an awful lot of work that's been done, mainly in the last 15 years, spawned by manufacturing. People are coming up with better mousetraps. The engineered products, the guys that come into your office and want to do brown bags, lunch and learns, leave the literature, the volumes of literature on your desk so that you spec their product in your plans. That's really what's driven what we know right now as far as the performance of vegetation and engineered products, intuition. Unsteady, we'll talk about in a minute, we know a good bit based on small scale modeling, but we don't have a lot of prototype knowledge because of the cost and the scale associated with getting that kind of data. Steady state, like I said, we understand pretty well. If it's a levee or a dam, water level comes up, water comes down the protected side for a given period of time, constant shear stress, constant velocity. We know we have negative pressure up here that can be an issue, but you tend to reach normal depth, fastest velocity, highest shear stress, what we can protect against. Testing-wise, again, through the manufacturing community, ASTM has a subcommittee of sediment and erosion control technology. I made the mistake of stretching in a meeting once, and I'm now the chairman of that subcommittee. We have 11 sections of all the different types of products that you can imagine for erosion and sediment control. Everything from the ditch check structures you have on your construction site to high-performance TRMs, mulches, tackifiers, the chemistry that goes into the polymers that we make the mulches that we're trying to treat burn areas with. There's ASTM sections in that subcommittee that dictate how it's manufactured, what the QA/QC is on it, how it's tested, and most importantly, how it's selected, so that as an engineer, a designer, or an owner, you have a set of go-bys to be able to determine what that best tool could be. The testing, as you well know, with sediment control or erosion has to be prototype. You can't scale that well, you can, but it doesn't work. That interaction between water and sediment and erosion very well. Very, very limited work you can get out of scaling. So it has to be a prototype application, whether it be an unvegetated or in a vegetated condition. The end of the game, of course, is the importance of finding where along your slope you have that, can't say failure anymore, so I think the buzzword is performance threshold, where you have too much sediment that's moved out, so that treatment, whether it's articulated block, whether it's vegetation, whether it's soil cement, lime stabilized clay, whatever it is, where it ceases to function, where you would be worried if it was your stamp on that job and you went out and looked at it and saw a gully. That's the performance threshold that we have to determine from testing, so we can get that value of shear stress or that value of velocity to put back into whatever design methodology we're using to compare against rock or to compare against native vegetation or these myriad of products that we have available to us. What it really gives us as engineers then is a summary table essentially of different types of treatments and what those permissible velocities and shear stresses are. Anybody size rock in their daily jobs here? There's enough rock sizing equations out there that we could each have our favorite with no duplicates. And it could probably hold up in a court of law as to why you picked that one. These types of treatments aren't that lucky. If they fail, it's done. So there has to be one method for an engineered product. For some reason, riprap, well, most DOTs consider riprap a temporary countermeasure, a maintenance issue, not an engineered solution. For engineered products, that's not the case. We need to be able to know what that threshold is so that when it's designed and implemented on our project, the attorneys don't just continually circle around the site every time it rains to try to wait to see something that's gone wrong. We have to have that definitive performance information to be able to implement it. Steady state, we're doing pretty good. With the exception of hydraulic jumps. Any of you that do anything with levees or dams or any type of embankment, there will be a hydraulic jump at the toe of your slope. We know nothing, be clear on that, nothing about hydraulic jump hydraulics. Now you can go to Chow's book and you can get the equation and put out on your piece of paper and what your jump length is and what your conjugate depth is. That's really nice. But we know nothing about the turbulence and the energy dissipation within those jumps. The Bureau makes stilling basins. Type 4 Bureau reclamation stilling basin, huge, massive concrete structure because we don't know. The risk of being wrong is much, much greater than the cost of concrete, so you throw a lot of concrete at it. For what we're talking about with engineered solutions as far as incorporating vegetation, we know nothing about what's happening in this area of hydraulic jumps. So it is still the area for steady state overtopping that there needs to be a considerable amount of effort put into. Unsteady now is when we have waves, of course, on top of that. Now it can be a situation where, in this case, the ocean or Lake Bourne, huge body of water, can see it from space, or small reservoirs, Horsetooth. You get the wind going in the right direction, you go, what, 4.5 miles of fetch? You can probably get 2.5, 3-foot waves that form on there during a storm event, just because of that depth and length of fetch. So it's the combination of waves on top of a steady state overtopping, or the waves just by themselves on the front side and on the protected side, that is really what Katrina alerted us to the deficiency in our design techniques. The reason we don't know a whole lot about this, as I said, most of the work that's been done with waves are in modeling basins, things a little bigger than twice this room probably, where you can generate waves and look at structures. Full-scale wave testing, this is the Delft Hydraulics Institute in the Netherlands, is not cheap. They can do it, but this guy just got the bill, and you can see what he thought. It's $250,000, $300,000 just to get in the door there to try to get anything done. So you can imagine for the manufacturing community to try to get information on their techniques, their products, their systems is rather cost prohibitive. So we don't have a lot of information on the effect of waves coming down the protected side of a structure, with or without that steady state component. What we do know from modeling, though, is helped a lot and get us to where we are today. We know that for every geometry of levee and storm condition on the flood side, there is a signature velocity and flow depth at the crest of that structure. So if we know the storms with the hindcasters are very, very good at getting the computer models, you've seen the ANSERT models where you can see the storm brewing and worst possible scenario of conditions. We know what that depth and velocity would be at the crest of that levee. We know that as far as the height of the levee, if I lower my levee for any given storm condition, I essentially increase my unit discharge. Makes sense. If my levee's up here, my storm level is here, I don't have a problem with steady state, but waves could still form. As I lower that levee, more and more water is going to come over for a given storm condition. So the trick for the designer, for levee owners, is to balance that. You can imagine a levee with a 4-to-1 side slope. That takes a heck of a footprint. So every foot you go up takes a tremendous amount of real estate that you just don't have in a lot of these areas. So being able to optimize what that height of that levee is to provide protection for whatever your design event is the trick to most levee design systems. So again, the hindcasters, the coastal modelers, are able to tell us that. They're able to say, okay, for this area, this geometry, here's what you can expect. Here's the storm, the number of waves in that storm that you're able to, that you can expect to be conveyed down that protected side. So the Dutch, when you've ever been to the Netherlands, it is completely below sea level, very, very far below meters below sea level. So a breach to them is the end of their country. It's not just a blemish in New Orleans history. It puts their country out of business. So they take it very, very seriously. Dr. Vandermeer has designed a device that he can take out to levees that simulates that depth and velocity. So when he takes his unit out, this is in Germany, takes his unit out and sets it up on the flood side of a levee, this grass on this protected side doesn't know that it's a nice, sunny, beautiful day and there's no water on the flood side, because the shape and the control of that simulator is mimicking that depth and velocity at the crest. So as it accelerates down the back side, it's a natural wave that's being conveyed. Has had great success in the Netherlands. You can see it's about a 3-meter wide flume, able to convey fairly large quantities of water, and then document the damage. Well, in 2006, when this really first started with post-Katrina, this was one of the ideas that we had was, okay, let's bring that device or build one here that we could then take down to the levees of New Orleans and test these systems and see just how resilient this clay and grass combination is. Well, you can imagine, the Corps liked the idea, but the PR of that was a little daunting because they really didn't want to find Jimmy Hoffa in the middle of the levee and also expose these levees to the damage that they would see for us to actually be able to learn anything. They didn't really know what was in some of them. So they pulled back from that field testing program. I'm either really smart or not very smart at all, but somehow we ended up with this project here at CSU and this drawing from Yancey's brother Gerben, who designs farm equipment, genius mechanical engineer. But this is the drawing we got of, okay, this is what you need to build to solve Katrina's problems. Went into it a little bit further, started putting together the pieces. The way it works, the simulator works, again, is that we have to get the water to come out of this tank. It's essentially taking kinetic energy and turning it into potential energy. So we have to get the right volume of water in that tank, release it from that simulator in the right period of time and with the right shape of exit so that we're able to, again, mimic that depth and velocity at the crest of the levee for every wave in that storm condition for every modeled height of levee. We had a great team of folks to be able to work on it, put it together in 3D software so that we could actually build it, have an inner tank, the different volumes you can imagine, I'll show you in a minute, that it can go from, we had to be able to simulate from 0.01 CFS per foot, which is nothing, to probably about 5 or 5.5 cubic feet per second per foot, which is a lot of water. I'll show you a large wave here in a minute. So the inside geometry of that tank was actually quite complicated to be able to get the right release of each wave volume, small, medium, and large, to make sure we had that signature depth and velocity. Outer volume for the bigger wave volumes, and then a set of trays. Now we couldn't take this to the levee, so we had to bring the levee to the laboratory. Really why it came to CSU is because of our experience with steady state overtopping. We've written most of the standards that we have for steady state interpretation of product performance or system performance. So we had to have a way to be able to actually bring the levees to us and place them in the simulator. We have 2 separate trays here. So what we ended up with was a device that gives us full-scale testing, 2 test channels so that we can expedite the process. Steady state capabilities also, because you can imagine in a lot of instances you'd have the waves that come over, but as that surge level comes up, you start to get the steady state coming down that protected side also. It's an exponential function of the stresses, how they increase with that. Some of the preliminary data we've looked at the break and slope that you have, you can see a 4, 5, 6 time increase in the shear stress. Velocity doesn't change a whole lot with the wave on top of it, but the shear stress, that pounding, is what really can cause things to reach their performance threshold very quickly. Certainly you had to instrument it. We know nothing as a research body or an engineering faction of what the shear stress and velocity is with the wave. I mean, we can sort of film it and measure it, but what's the effect of that? How does that, I know if I have 6 feet per second, I can take whatever your favorite rock sizing equation is, EM6